Okay, welcome to Module 9, and this is the topic of Module 9 is a topic that's near and dear to my heart. You may know, or you may wind up discovering, that I'm an amateur musician. I like to play a couple of different instruments and write songs, mostly about science. And in fact, who's that guy? That's me when I was much younger. But I do play several stringed instruments, including the banjo, the guitar, the mandolin. I also play a harmonica, as you can see around my neck. And I've even more recently taken up the piano accordion. So I really enjoy music, not only because it's just aesthetically pleasing, and I enjoy the process of learning something new, but it's a good application of physics. And so it's another way of tying physics into my daily life and into my hobbies. And that I find very, very fascinating. The study of sound is actually a branch of physics called acoustics. And I mostly play acoustic instruments. I don't amplify myself very often, but I really find it very interesting to learn how sound is created by, let's say, a vibrating string, in the case of stringed instruments, or in the case of a harmonica or an accordion, it's actually a vibrating reed. But it starts with vibrations. And that's one of the first things you're going to learn about in the notes here is vibrations and how you can characterize vibrations with frequency and wavelength and wave speed. So make sure you pay very close attention to that. And then as we get into the later part of the notes, make sure you pay attention to things like interference. Okay, waves can actually interfere with each other constructively or destructively. And for example, when I'm tuning my guitar, I'm actually listening for that. I will tune my guitar and listen for what are called beats. I want to listen for constructive interference and destructive interference in order to tune my guitar. So anyway, it should be a very, very interesting chapter. I hope you enjoy it. A spring or a slinky with a weight on the end is actually a good way to think about vibratory motion or oscillatory motion. Let's imagine we have a little slinky here, and attached to the end of it is a little weight, and we've got it hanging here, and we let it hang to the point where the mass at the bottom is motionless. And we can think about, okay, what are the forces acting on that object if it's not moving? Well, of course, we would have the weight of the object itself. So there's downward motion, there's this downward force we would call weight. And there's an upward force. There's a tension here that's produced by virtue of the fact that we've stretched this spring to a certain amount. We all know that springs like to be a certain rest length. And if you start to move them from that rest length, they don't like it. If you stretch them, they snap back. If you squeeze them, quite often they push out. They like to be a certain length, and if you change that, what's called the rest length, you're going to have what's called a restoring force. So in the case of attaching this weight to this slinky, it's going to, if we just let it go, it's going to stretch to a certain length. And once it's stretched to that certain length, there's going to be enough tension that it'll equal the weight, and so therefore the object is at rest. Now let's imagine that after it's come to a nice rest position, now we go ahead and we pull on it. We tug downward on the, I give this guy a pull downward. What's that going to do? It's going to stretch my spring beyond the rest length. And by doing that, I'm going to have an upward tension force that's larger than my weight downward. Again, I give it a little push to get it going. Once I give it a push, though, I let go. So I'm no longer pushing. And so therefore, what we see is that, okay, I'm going to have an overall upward net force. That's going to slow my mass down until eventually it comes to a stop at the bottom. But when it comes to a stop at the bottom, I'm going to have a much larger upward force than I'm going to have a downward force. And therefore, now my ball is going to accelerate upward until it gets to the point where my spring gets kind of squeezed. And at that point, again, I'm going to have weight acting downward, but now I'm going to have a restoring force of this squished spring that's going to be also acting downward. And so I'm going to have a net force that's downward. That's going to slow my ball down. It's going to bring it to a stop. It's going to start moving it downward. And so this ball is going to essentially go up and down, up and down, up and down, over and over again. Now that is vibratory motion or oscillatory motion. Now imagine as my ball is doing that, which we can picture here, the ball's going up and down and up and down. Now imagine that we have a little pen attached to that ball, and we have a piece of paper, and that paper is moving in this direction. It's kind of like the passage of time. So even though this ball appears to be moving just up and down in one dimension, we can imagine if we added on the dimension of time, passing time, that we would wind up with a wave looking drawing here, where the ball would move through its highest position, it would move to its lowest position, and back to its highest position. So again, we see the wave nature of this vibratory or oscillatory motion. So once we understand that a ball on a spring can actually create a wave, let's talk about some of the wave terminology. Well, first of all, the very tops of the motion, that's what we call the crest. So here's a crest, here's a crest. I've done those in blue. And in red, I might want to draw in what are called troughs. These are your low points. And it turns out that one important piece of wave terminology is the distance between a crest to a crest, or it turns out a trough to a trough. It really doesn't matter which you choose, but that distance is what's called a wavelength. Okay, some more jargon for you. Amplitude. Now, amplitude is the distance from the midpoint, the green line here, to either the top of the wave or the bottom of the wave. From the midpoint to the crest or the midpoint to the trough, either way, that's your amplitude. And one thing you'll learn about amplitude is, we'll think about how would I make this wave taller or shorter? Well, it really depends upon how hard I pull on the ball to begin with, right? If I really pull on it or give it a good push downward, I'm going to create a wave that's going to have a pretty big amplitude. It's going to do what it's doing here in the picture. But imagine that I just barely give it a little shove. Then can you picture what would happen there? Turns out I wind up with a much smaller wave. I'd wind up with something like this, also in blue there. One thing, what do you notice about it's not a perfect drawing, but of my new wave that I just created? Turns out that the spring, or the wavelength of the wave that I would create is going to be the same, but the amplitude different. So again, I give it less of a force, and therefore I'm going to have less of a displacement from its midpoint. However, it turns out that the wavelength of the wave that's going to be created is going to be the same. And again, if we go back to our vibrating spring example, we got a little mass on the end of a spring, we can understand another very important term in wave motion, which is frequency. So if you imagine you've got the little ball on the spring and you give it a shove down or a tug downward, and it bounces back, and it's going to go through a pattern where it's going to go up and down, maybe to these extremes. The time that it takes, or the number of cycles, remember that it's going to be moving up and down. And if we see how frequently it goes from its bottom position up to its top position and then back to its bottom position, that is what we call one cycle. It has gone through one full cycle of its motion. And if we count the number of cycles that occur every second, that is what's called frequency. So it turns out that frequency, it's usually given as an F, is cycles, the number of complete cycles that vibratory motion goes through in a second. Cycles per second, which typically is abbreviated. That unit there, cycles per second, is usually abbreviated as hertz. HZ is the abbreviation there. So frequency is given in hertz, and one thing that I have not mentioned to you yet, or should have, is that wavelength, which we've already talked about in the last couple of slides, is given as a Greek letter called lambda, but again, that's equivalent to wavelength. And notice that the units of wavelength are going to be the units of a length, which typically would be like meters or centimeters or something of the sort. But again, in physics, you'll usually see wavelength written or abbreviated with a Greek letter called lambda. That stands for wavelength, and that's going to be in meters typically, centimeters, any kind of distance unit. So hopefully you've picked up on the fact that frequency and period are inverses to each other. So we've already talked about frequency, again, F, as being cycles per second. Cycles. Well, it turns out the period, which is usually given as a capital T, is just the inverse of frequency. So you actually figure out the period of a wave or of a oscillatory motion by taking 1 divided by the frequency. So it winds up being, you're just flipping the units here. So it's seconds per cycle. It's how long does it take for the vibrating object to go through 1 full cycle of its motion. So they're inverses of each other. This is actually a very good skill builder to get you familiar with waves and some of this wave terminology we've already been talking about. The simulation actually allows you to add waves, but my suggestion is to, first of all, turn off every wave except for one. Just leave wave 1 on there, and then play around with changing the amplitude of the wave and change its frequency as well. You may not want to mess with the C value. That's actually the phase shift. Leave that alone at 0 for the time being. Just get familiar with what happens when you change the frequency, what happens when you change the amplitude of wave 1. Then once you're comfortable with that, you can start adding in extra waves and seeing how they interact. Because it turns out, as we're going to get to here in the notes, you can actually have waves that add together or waves that can kind of subtract off of each other. And that's what's called wave interference. You can either have constructive interference or destructive interference. And so if you want to explore those possibilities, that's when you want to add in some extra waves, add in wave 2, add in wave 3, see how they add together. And there's where you can also play around with the phase shift. Because obviously if they're all in phase with each other, they're always going to add. You're always going to have constructive interference if all your waves are in phase with each other. But if you put 2 similar waves but make them a little bit out of phase, changing the phase shift, then they're going to perhaps have some constructive or some destructive interference as well. Okay, so you're going to actually come across a mathematical relationship between 3 of these wave characteristics: frequency, wavelength, and wave speed. So imagine you're this bird sitting on this little perch out in the ocean, this little pier, and the waves are lapping along right along your little pier, your little perch there, and you're watching the waves, and you're counting the number of wave crests that are passing by every second. Well, it turns out that you would have 1 wave passing by every second in this scenario here, because the frequency we're told by these waves is 1 hertz. That means that your wave goes through 1 full cycle every second. So therefore, you have a crest that hits the pier, and then the trough moves through, and then another crest hits the pier within 1 second. So it goes through 1 full cycle in a second. That's what's called a hertz. And of course, they also tell us that the wavelength, this distance between the crest and the crest, is 1 meter. And so it turns out that our wave is essentially moved 1 meter in 1 second. And so therefore, we are told the wave speed. This wave has a speed of 1 meter per second. Okay, here's a good place to kind of catch our breath and to think about things, and think about fictions before they perhaps fester into facts. Let's think about how we hear things. You know, I've got my listener and I've got my speaker, right? It's very important for you not to get the impression that a sound wave goes from the speaker to the listener's ear like this. Like there's only 1 single sound wave that's created by the speaker. And that would make no sense, because that would mean that only 1 person in a classroom of 30 would be able to hear the speaker. That's not the way it works. It turns out that the speaker's vocal cords excite air molecules. They create what are called compressions and rarefications in air molecules. And that by exciting the air molecules close to the speaker, those air molecules then bump into neighbors, and therefore the wave winds up being transmitted outward. But it's not just one single wave. It's actually, sound waves are going off in every direction from the speaker. That's why, and of course, that's it means that the room is full of air, and therefore that energy is being taken off in all directions. And if you happen to be sitting in the room, you're more likely than not to be able to hear the speaker, because those compressions and rarefications of those air molecules are going to wind up hitting your eardrum. Your eardrum's going to start to vibrate, transmit, and then turn that vibrational energy into mechanical energy, and then eventually into electrical impulses, which your brain interprets as sound. This is actually a very good question, because it makes you think about how sound travels. Sound waves have to travel in a medium. They have to travel through, in this case, it's air. We're going to imagine that this opera singer is singing, and the energy from her vocal cords is being transmitted through the air to all the different members of the audience, including this guy up here. But think about how he's also hearing this opera singer. He's also hearing the opera singer because her voice is hitting this little microphone. Once her voice hits the microphone, her voice is no longer being transmitted as a sound wave. It turns from a sound wave into an electrical impulse. That electrical impulse goes down the cable, out the door to perhaps a satellite van sitting outside, which transmits the signal up to space. There's the satellite, beep, 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 beep. Again, as an electromagnetic wave, and of course hits a satellite. The satellite transmits it down to the radio station. The radio station has a tower outside, and that tower transmits the signal off in all directions, and eventually gets to this guy's antenna, and that antenna then vibrates and turns into a sound signal, which then he hears in his ear. So notice that even though it's a much longer trip for the sound to get from the woman's voice into the microphone, from the microphone to the sat truck, from the sat truck to the satellite, from the satellite to the radio station, from the radio station back to this guy's transistor radio, it's making most of that trip at the speed of light. It's moving as an electrical impulse, and an electrical impulse travels at the speed of light. Whereas her voice, heard live in the auditorium, travels as a sound wave from her position on the stage all the way to the guy in the audience. So the question is, how is he going to hear her voice first? Is it going to be live because of the sound wave traveling from the singer to his ear, or is it going to be through the radio as the sound wave actually becomes an electrical impulse, traveling a much greater distance, but also traveling at a much greater speed? Now, you probably read in the book that there is a difference between light waves and sound waves. Sound waves require a medium, and usually we talk about that medium being air. And so sound travels at the speed of sound through air. But it turns out that the speed of sound is not one fixed value. It does change depending upon the conditions or the material that the sound is moving through. It turns out that in air, we say that it's got a speed of sound in air. That's actually room temperature air. It's about 340 meters per second. That's the speed of sound. But it turns out with warmer air, sound travels more quickly. And certainly in different media, sound travels much, much more quickly. In fact, in water, as you can tell from the PowerPoint slide, in water, sound travels 4 times more quickly than it does in air. And in steel, a solid, it travels 15 times more quickly. And that's because if you think about the difference between a gas, a liquid, and a solid, in a liquid and a solid, the molecules are much, much closer together. And that's what you're really needing in order to have sound transmitted. It's got to move from one molecule to the next. And so therefore, the more tightly bunched molecules are, the more quickly and more efficiently they're going to transfer energy from one to the next. And therefore, in a solid, you're going to have the greatest efficiency of transmitting the sound energy, and therefore the sound's going to travel much more quickly in a solid than it will, say, in a gas. Did you ever see the movie Alien? Do you remember what the tagline was for that movie? And most importantly, what does any of this have to do with sound or sound waves? Well, I've got a tennis ball here, and again, that doesn't have much to do with sound either, except this is a special tennis ball. It's got a buzzer. Notice when I turn the buzzer on, the sound from that buzzer is reaching the microphone because it's being transmitted via sound waves. That's getting annoying. So let me put this bell jar on there. And once I put the bell jar on, notice that that cuts down on the sound quite a bit. But if you listen close, you should still be able to hear a very faint buzzing sound. Of course, this is a bell jar, and it's connected to a vacuum pump. So what I'm going to do now is I'm going to use the vacuum pump to take the air out of the bell jar and remove the air that's going to surround that tennis ball. And we'll see what that does with respect to sound and sound waves. Make sure I get a nice good seal here, so I'm going to add a little grease around the edge of my jar. And that's probably pretty good. I think I've got a pretty good vacuum going here. Again, the vacuum, all it does is it just takes air out of the bell jar. So where there once was air, there's no longer air. Let's see now, of course, what you're hearing right now is mostly the motor from the vacuum pump. Let me turn that motor off real quick. Listen real close. Do you hear anything? I don't. But let me go ahead and now undo the vacuum. I've got a little valve here that's going to let the air back into the bell jar. Now what do you hear? You should hear the buzzer again. What was the tagline to that movie? In space, no one will hear you scream. What does it look like inside of a recording booth, inside of a music studio? Do you ever notice? There's foam hanging up on the walls. In fact, that foam has a special kind of shape. It's usually kind of an egg crate shape. Well, what is that for? It's not used to keep sound from coming into the booth from outside. It's not used to soundproof the room. What it's used for is to minimize the amount of echo that occurs within the room itself. So let's say you've got a vocalist who's singing into a microphone in one of these little recording booths. What you want to capture is the voice of the singer going directly into the microphone. That's the desired sound. What you don't want, of course, is that voice. Not only does it hit the microphone, it goes in all directions and it hits the walls. And what you don't want is you don't want the voice reflecting off the walls and bouncing into the microphone as well. You want to have just one signal straight from the person's mouth. You don't want to have a bunch of reverberation or reflection or echo. And that's what the soundproofing in the foam soundproofing does, is it either absorbs the sound waves that hit it, or it reflects them in other directions, multitude of directions, so they don't all go straight back into the microphone. So sometimes an echo is desired, and therefore you would have a nice flat surface, but if you don't want an echo, you would have a very uneven, rough surface. And it turns out this is the same thing that goes on with light as well. So think about on a dark night, when you've got your headlights on, first of all, you can see the road, right? Well, why can you see the road? Not because the road is producing its own light, but because the light that is shining from your headlights is hitting. I'm going to draw on it. It's going in this direction down toward the ground, and it hits an uneven surface, and some of it winds up being reflected back up into your eyes. However, what happens on a dark and rainy night? On a rainy night, you get a little layer of water forming on the roadway. Essentially, it fills in all those nooks and crannies that your road surface usually has. And therefore, a light beam coming from your headlight, instead of hitting a nook and cranny and bouncing back toward you, winds up hitting and reflecting almost perfectly down the road, which does you no good in actually seeing the road. That's why it's so very difficult to see the road, because the light that your headlights are providing is not being reflected back into your eyes. It's being shot off far in front of you. So reflection can be a good thing, and sometimes not such a good thing. I occasionally like to include graphics that I designed years ago when I worked at USA Today when it illustrates a point. And the point I'm trying to get at here is that when lightning strikes nearby, you hear an immediate smash. You hear a loud crack, a very just one single sound. But when lightning is much farther away, you don't hear that distinct crack. You hear more of a rumble that can actually go on for several seconds. And the reason for that is because the sound does travel in straight lines. It can sometimes take a circuitous path to your ear. So for example, you could have the rumble that comes straight from the lightning, but then of course the sound wave that's being produced when the thunder occurs heads in all directions, and some of that sound takes a much longer path to get to you. It might bounce off buildings, it might bounce off mountains, but it eventually does reach your ear, of course traveling at the same speed. So it travels at the speed of sound, but it goes a much longer distance, therefore it takes a longer time to get to your ear, and that's what prolongs the rumble of the thunder. Okay, so check this out. This is probably a familiar object to you. This is a tuning fork, and notice that it's not doing anything right now. It's not making any noise. But when I strike it with a little mallet here, notice that you hear a tone. In fact, if you look really carefully, and you probably can't see it from your perspective, but the arms of the tuning fork are vibrating. And by vibrating, they're moving air molecules, and that's what's actually, that's how the mechanical energy of these vibrating pieces of metal winds up reaching the microphone and then eventually reaching your ears. Let me do that again. Can you hear it? Let's see if I can make it a little bit louder. Can you hear it now? This is a difference when I let the tuning fork vibrate all on its own, and then bring it in contact with the desktop. Turns out that the vibration of the tuning fork forces a vibration in the desktop. Of course, the desktop is much larger, and therefore it can vibrate more air molecules, and therefore you wind up with a louder sound. Now that was a C tuning fork, had a certain pitch. Let me try a different tuning fork. This is the same note. This is a C as well, but this one is 512 hertz. This one was 256. So let's see if you can, or 260. Let's see if you can notice the difference between the two sounds. They're both C's, right? The one just has a higher pitch. One's lower, one's higher, but they make the same note. Now, let's see if I have a different note. For example, a G. This is a G tuning fork with a frequency of 384 hertz. Different sound. Still higher than this one. And now I get a G note from that one. So tuning forks have a specific frequency of what's called a resonant frequency. When you hit it with a hammer or a little mallet, it's going to make those arms vibrate, but they vibrate at a specific frequency. In this case, 384 hertz. In this case, 256 hertz. So I hooked up a microphone and recorded a C tuning fork and wound up with this sound wave. And again, what you can see here is we're mapping the sound pressure on the y-axis. We've got time on the x-axis. So what's happening is the microphone is picking up these compressions and rarefications of these air molecules. So when the microphone diaphragm is really being pressed on, you have a high point in the graph, a lot of sound pressure. And when it's not being pressed on very much, when it's going through rarefication, you have a low point in the pressure graph. And the important thing to illustrate here is that with a C tuning fork, you get a nice, essentially a sine wave, this nice up and down, very regular kind of pattern. And what we can do is we can actually pick out one of these peaks and pick out the next peak. And what we can do is we can actually look at the amount of time that elapses from peak to peak. Remember, that's a piece of terminology you should be familiar with. The amount of time it takes for a wave to go through one cycle is something called the period. We abbreviate that with a capital T. And so the period of this wave, in fact, I could actually pick out the time values, it winds up being about 0.019 seconds. So the time it takes for this wave to go from peak to peak or from trough to trough is about 0.019 seconds. Now, if you recall, if I wanted to find out the frequency of this, all I need to do is take the inverse. Remember, frequency is the inverse of time. So if my period is 0.019 seconds per cycle, so for one cycle it takes about 0.019 seconds, I can invert that to get my cycles per second or my hertz. And it turns out it's in the ballpark of, I think actually if you do the math here, it's 526. Of course, that's just choosing one of these waves. I'm going to get different values, slightly different values, if I take the period between the next two peaks, so forth and so on. But on average, if I averaged all those periods up and got the frequencies, I'd wind up with essentially 512 hertz. So I was able to confirm the frequency of this tuning fork by doing a few measurements on its wave pattern. Resonance is a very interesting topic. Now, one way of illustrating resonance is to think about, let's say, a child on a swing. I've got 3 kids and they like to ride on the swings. So you got a kid on a swing. Okay, and so what do you do as the parent or the pusher if you wanted to make that child swing higher? You exert a force on the child, but you don't do it like all the time. You actually wait until, notice that the swing is going to go up to this high point, and it's going to swing back to this point. And of course, you don't, when the child is swinging, let's see, let me put some arrows in here. When the child is swinging back toward you, you don't push them when they're at the low point. You wait till they come all the way back to the highest point back toward you, and you give them another push. So you have to time the force. You have to time when you apply your force. You don't just apply it randomly. That's what we call resonance. If you really want to make the child swing higher, you have to kind of be in time with their swing. You only apply a force when they're back closest to you at their high point. If you were to apply a force when they were coming back toward you, let's say at the lowest point, you would actually cause them to stop. So you would not be in resonance there. So you'll actually see some debates online about the example given in the book, this Tacoma Narrows Bridge. It may not be a perfect example of resonance. The reason being, yes, the wind had played a factor, very big factor in this, but notice the wind was blowing the entire time. It wasn't like starting and stopping and starting and stopping the way a parent would be pushing a child. So whether this is truly resonance is very, very much open to debate. The important thing for you to understand is that resonance is when you are applying a force periodically, and that period matches the period of the resonating body. All right, frequency fans, I've got a pretty cool apparatus here called a resonance tube, and we're going to give you a little demonstration of what this thing's going to do. Now I have a C tuning fork. It's got a frequency of 512 hertz, and we all know what happens when I hit it. You hear a nice tone. And what I can do is I can put this tuning fork over this tube, and this tube is it's a glass tube that I filled mostly with water, but there's actually a little bit of air here. And by putting my tuning fork close to the top of the tube, it's going to excite the air molecules in that column of air. And what we notice is that it doesn't really make a big difference when I put as far as the volume of the sound right now. There's no big amplification. We don't really detect any constructive interference going on. But let me make one change. What I'm going to do is I'm going to put my tuning fork over the top of the tube, and then I'm going to change the level of the water. I'm actually going to increase the size of the air column here, and we'll see what happens. Listen for any changes you might hear. Did you hear that? Let's try it one more time, just in case you missed it the first time. I'll let my water come back up to its original level. Remember, I'm going to create waves using the tuning fork. Those air molecules are going to be excited in all directions, including down the tube. And we're going to hear sort of a magic moment when the wave that's being sent down the tube, of course, the wave hits the water surface and reflects back upward. Quite often, the wave going down and the wave coming back up interfere. But every once in a while, you have the wave that's coming back up that matches the phase of the wave going down, and that's when they add together. So notice the tone doesn't change. We still have that C sound, but the volume increases. The amplitude of the wave increases because of constructive interference. Check it out. There it is. The resonance tube. It's pretty cool. I really encourage you to play around with this skill builder. It's really cool. You get a chance to actually hear beats. You can build waves that have similar frequencies and have them in phase and see what that does when you add those waves. Or you can build some frequencies that are very much out of phase and see what that does. To me, it reminds me very much of when I tune my guitars. When I tune my guitars, I actually try to create the same frequency on two adjacent strings, and if they're perfect, then I hear just one tone. But if they're not quite right, I'm going to hear what are called beats. They're going to be a little bit out of phase. And so this is a really cool skill builder to let you play around with wave interference. Again, this is another graphic that I dreamed up during my USA Today days. And a lot of folks don't realize that radar was first invented back in World War II for military purposes in order to spot planes. And so you would shoot out a microwave pulse and wait for that microwave pulse to be reflected by an object and then return to the place where you sent it. So you would emit it and then you would also receive it. And the time elapsed between when you send out the pulse and when it gets reflected and when it arrives on its homebound journey If you measure that time, and you know, of course, that these things are traveling at the speed of light, because they're forms of electromagnetic radiation. If you know the time that it took for the round trip, and you know the speed that the wave is traveling, you can figure out the distance. It winds up being just the speed of light times half the round trip time. You can range how far your object is away, and that's what a radar actually stands for. Radar detection and ranging, or radio detection and ranging. But what people quickly realized was that they would notice a shift in the frequency of the returned pulse. So the pulse would go out at a certain frequency, but it would come back with a slightly shifted pulse. And well, first of all, quickly the military realized that they could not only pick up planes, but they could pick up birds and even raindrops. And that really became important in double purposing radar for weather. Because once you knew you could actually see raindrops, well, that's really important because you can tell how far away rain is. And even more importantly, it was the fact that, again, by hitting these moving objects like raindrops, there would be a change in the frequency of the return pulse. And by measuring the amount of change in frequency, how much Doppler shift is going on, you would be able to figure out how fast the winds are within that storm because of how fast the raindrops are moving. And so if the raindrops were moving away from the radar site, you would get a red shift. If the raindrops were moving toward the radar site, you'd be getting a blue shift. But in any case, it's the Doppler effect that made radar so much more important. It's great to know where the rain is, but it's even better to know the wind profile within the storm so that not only can you pick up rain, but you can also pick up the potential for severe weather like downbursts and tornadic activity. Of course, as a meteorologist, you always have to be very careful about what your radar is showing you. Sometimes your radar is showing you stuff that either is not there or is there, but it's not weather related. So because radar can pick up on things like birds, you can pick up roost rings early in the morning as birds are leaving a particular location. You will start to get echoes from the radar site, and that's due to the radar beams hitting birds and being reflected back to the radar site. You can also get a sun spike. At sunrise, when the sun shines right on the radar site, you're going to get a flood of electromagnetic radiation, which shows up as a sun spike. Or you can get ducting, which has to do with the refraction of your radar beam, where it actually is hitting the ground rather than actually hitting rain droplets that might be in the air. Okay, so I'm going to try to illustrate the Doppler effect by using this. It's actually a little bell, or notice that with a certain frequency when the ball is stationary. But I'm going to swing the ball over my head, and you should hopefully notice the difference in the pitch as the ball comes toward you and as it goes away from you. So again, this is the at-rest frequency. Do you hear a difference? That's the Doppler effect. And one thing that's very important to understand about the Doppler effect is that the Doppler effect applies to anything, any waves. So that includes sound waves like you just heard, but it also would include any other type of wave, including light waves, not just visible light, but all the different frequencies in the electromagnetic spectrum. Oh, hi there. Do you ever wonder what makes music sound so interesting? so interesting to the ear? And what makes musical notes different on different instruments? It turns out that it has to do with overtones and extra frequencies, not just your standard frequency of a particular note, but on different instruments you're going to get different overtones, changes in the waveform, which makes it sound different from one instrument to another. For example, I'll play a G, a low G note on this mandolin. Unlike a tuning fork, which has a relatively standard sine wave pattern, as you can tell, the wave pattern for the mandolin is much more complex. In fact, you would be hard-pressed to pick out a sine wave from which to calculate the period and the frequency. So another way of analyzing a wave as complicated as this is by using a tool called a fast Fourier transform, which picks out the important frequencies that make up that wave pattern. And that's what we see here. We see a fast Fourier transform of the mandolin G note. And what you see is that we have a G as the peak frequency, 781 Hertz, but there's also a variety of other frequencies mixed in there. That's what makes such a very interesting sound. This is the banjo G note. Same pitch, but it sounds different to our ears. That has to do with extra frequencies, or what are called overtones. When we record the sound with a microphone, what we get is this sound wave. It's a sound pressure graph, sound pressure on the y-axis and time on the x-axis. And what we see is that the diaphragm in the microphone is experiencing those condensations and rarefications, those air molecules that are pushing up against it and then not pushing up against it. And so we see a signal here. And it has some periodicity, but it's not a simple sine wave. It's much more complicated than that. And that's again why we have to apply a fast Fourier transform to pick out the important frequencies that the microphone is experiencing. And again, the peak frequency we have here is that G note, 781 Hertz. Try your old trusty guitar. G note on a guitar. And we again see a relatively complex wave pattern. Why complex? Because it's not just the string that is vibrating when you play a stringed instrument. It's several different pieces of the guitar. The soundboard, the body of the guitar itself. There are many things that are vibrating and therefore causing air molecules to move. And it's that combination of different frequencies that make up the sound that is unique to the instrument. Let's play a G note on an accordion. This would appear to be the most complicated pattern of all. It's really tough to pick out a sine wave, but we do see that there is a periodic nature to this sound wave. And part of the reason for the complexity here is because instead of playing a single note, I was actually playing a small chord on the accordion. But again, it winds up resolving to be a G note. But again, it's the same tone, same note. We can hear it in our ear, but it sounds different from one instrument to another. That's why we have other instruments, because they all have these unique sounds, and those unique sounds are all due to the wave pattern that is set up by the different instruments.